Hello, everybody. So we're still talking about the atom and the or the exploration of the atom and the atomic structure. And the last thing we found was that using the gold leaf experiment, we were able to figure out that the atom is not as was predicted before or thought before. It has a lot of space, and there is a very, very small nucleus and very, very small electrons, and the most of the volume is space. But there were some observations that were not explained well, and with this model, the last model that we talked about before, which is the Rutherford's model, there are still some observations that were not explained well. The most two famous observations were the one related to the atomic mass. So the way the scientists calculated the atomic mass is that they calculated the atomic mass of hydrogen, which is just a proton, and the atomic mass of any other element, which should be, as the model predicts, just protons, because the electrons have very negligible mass. So it's mainly protons. And it will have an integer number of protons, 2, 3, 4, 500, whatever the number, but it should be a real number, or I mean an integer number. So if you divide the mass of all the protons divide by the mass of one proton, you should get an integer, a positive integer number. But this is not the case. In many cases, we got fractions. So you could, in case of chlorine, we get the atomic mass of 35.5, which was very, very weird. We couldn't explain this using the current model. The second thing is that the mass of the protons that we know, so we know the number of electrons, and this number of electrons equal to the number of protons, and then we can calculate the mass of the protons, which should be, if the model is right, then should be equal to the atomic mass. But we always get the atomic mass kind of almost double the mass of the protons. So there should be something that we don't know in the atom that causes these two observations, or is responsible for these two observations. Rutherford predicted that there are some neutral particles in the atom, and he couldn't provide any evidence of this, but he just predicted this as the only explanation for these, or it's mainly for the second observation, not the first. So it was just some hypothesis until 1919, when the genius scientist Francis Aston started to do the experiments to modify the cathode ray tube. So he was doing the same thing with his new equipment. So it's called the mass spectrograph. So it's kind of very, very close in theory to the cathode ray tube. But what he did is he got any gas like chlorine, and then he ionized the gas, so it's totally free of electrons, and then he has the ions. But in the cathode ray tube, if you remember, we had this violet or purple glow that was glowing in the whole area, or the whole volume of the tube. But in his case, he forced the ions to go between or through these slits. So it's, instead of having this as a glow, it's just a beam. So he can get the chlorine ions to go in a straight line as a beam, and these ions, or this ion beam, can be deflected. So he can change the magnetic field that he applies here, so he can deflect the ion beam. And this is what you see here. This is the actual machine, or the main the first mass spectrograph that he made. And you see this huge coil there, and this huge coil is an electromagnet, and he can adjust the magnetic field to adjust the angle of deflection, or change the angle of deflection of the ion beam. So he can do kind of similar calculations to what we did before. He can calculate the magnetic field and the force that is caused by the magnetic field, and then do the calculations to get the mass of the atom. atom. So it was kind of very close in calculations to the previous ones that we mentioned before. And then he has this, it's not a detector actually, so this is the mass spectrometer, which is the modification of the mass spectrograph, but this is just a photographic film, so he can see the spot where this beam falls on the photographic film, and using some simple geometric calculations, he can calculate this angle and do the rest of calculations. So it was a breakthrough at that time because it gave very accurate results, and he did it for many elements. And the reason it was a breakthrough because in all the cases he used very pure elements, so he can get accurate results. But in some cases like chlorine and in neon, it was mainly in neon the first time. He always gets, so this is what he sees on the photographic film, just this very huge spot here, or the big spot here. This represents the place where the ion beam hits the photographic film, but he sees this small spot on the side. So it seems like the beam is not going on a specific place. There is some deviation from the original beam. And in the beginning, he thought there might be some impurities that cause this deflection, and he used very pure neon, and still he gets the same results. And this was the first time to know, or for us to know about the isotopes. So isotopes is simply two identical atoms. They have the same chemical properties, but one of them has higher atomic weight. And the atomic weight, again, let's put it this way: we have the same number of electrons in all of them, so we have the same number of protons. So the protons is the same in both the heavy and the light one. So there must be some other component in the nucleus that is heavy, which is comparable to the protons, or the weight of protons, and has no charges because it's already neutral with the protons and the electrons. And then we still don't know what is this thing, but there is something inside that causes the change in the atomic mass, and we call them isotopes. And this guy got the Nobel Prize for his great discovery. And the mass spectrometer is now just a modification of this. It's mainly here because they put here a detector, and this detector calculates the counts, how many ions hit the detector, and gives peaks of different elements, and you can get the atomic mass accurately using this technique. So this was the one of the things that kind of gave us solid evidence that there is some, what we call now, the neutrons, and in the same time it gave an explanation why we get this 35.5. We have chlorine 37 and 35. We'll get to this in a few minutes. Then when the solid evidence of the neutrons was got when in 1932, when James Chadwick did his experiment on beryllium. So he used the alpha particles to hit beryllium film, and he was just trying to see what will happen. And surprisingly, the experiment led to the formation of new elements. So it was beryllium. After being hit with alpha particles, it turned to be carbon. And he noticed that there are some powerful particles that are kicked out from the other side of the beryllium film. He exposed them to magnetic field, to electric field, no deflection, nothing happened. So they must be electrically neutral. He used the paraffin wax film. So the paraffin wax is very rich in protons. This is kind of a polymer that has a lot of kind of bonds between the carbon atoms. So it's kind of very rich in protons. So when this beam, so we didn't know anything about this beam, just that it is electrically neutral. And when it hits the paraffin wax film, it kicked out protons on the other side. Just to give you a feeling, so think of the protons as like a basketball, and the electrons as a table tennis or a ping pong ball. So if you hit a tennis ball, a basketball with a very small ping pong or the table tennis ball, even as hard as you can, it's not gonna move it, because the basketball is way bigger than this small thing. So to move the basketball with another ball, you have to hit it with another basketball. So it's or a football, some big thing that will be would have high inertia enough to kick this off. So this cannot be electrons because it's neutral for the first thing, and the second that it's not as big as the protons, so it's not gonna be strong enough to kick the protons out. So we knew that it's neutral, and we know that its mass is comparable to the mass of protons. So this must be the element or the part of the atom that is responsible for this mass that we don't know where it came from. With doing some balance on the equations, we knew that beryllium has it has four protons and its mass is 9. Helium has 2 protons and its mass is 4, and the product is carbon, mass of 6, and the protons of 6 and mass of 12. So we have 4 protons plus 2 protons, it gives us 6 protons. So our protons are now all going into the carbon atom, but we have 9 plus 4 gives us 13. So we have only 12 here in carbon, and there is one extra part of this thing that we don't know anything about. And then at this time we knew that this is the proton, this the neutron, this is the part of the atom in the nucleus that is responsible for the extra mass, and that's different from one element or one atom to another in the isotopes. So it doesn't have any contribution on the chemical properties, but it makes the atomic weight different. So just to talk about the isotopes, so let's to understand how the atomic weight is got as a fraction or it's not an integer number. Let's say for chlorine, we know it has 17 electrons and it has 17 protons and the 18 neutrons. So if we calculate the atomic mass, it's gonna be 35. But as we said, we calculated or we measured it to be 35.5. So it was found that there are like 25% of the chlorine is another form, another isotope that has 20 neutrons. So 20 plus 17 is gonna give us 37. So if you get the average, the weight average between 37, which is 25%, and 35, which is 75%, the rest of the chlorine, it's gonna give us this 35.5. And this explains why we get this difference, and that's why we now write the element in this form. Any element, write 2 numbers: the number in the bottom, which is the number of protons, and the number in the top, which is the number of protons plus the number of neutrons. So this is the isotope, and this is the other isotope. So until now, the scientists kind of used to use the atomic mass as the way to differentiate between the elements. This is the main property of the element to differentiate between them is the atomic mass. Until this genius guy started to do his experiments, he was not kind of convinced with the atomic mass. And he was trying to prove that the atomic number, which is the number of protons, is the characteristic property of the elements. So his name is Henry Moseley. In 1913, he developed his law, and he said that the elements are kind of arranged according to their atomic mass. It's not the atomic number. You have isotopes, you have different atomic masses, and it's gonna be kind of messy. So if you use the atomic number, it's gonna be very sharp difference between the elements. And he did the experiments using the X-ray that is radiated from the elements from the cathode ray tube. So he said that if you put the element in a cathode ray tube, and this is how they explored the X-rays, is that this was radiation coming out of the cathode ray. So if you get the X-rays coming of the cathode ray tube from different elements, you can get calculate the frequency of this X-ray. And if you plot the square root of the frequency of the X-ray against the atomic number and against the mass number or the atomic mass, you see that for atomic number, or it's gonna very nice straight line. It's it's almost perfect straight line. But for the atomic mass, you'd see that it's going up and down, up and down. It's not kind of reliable as it is for the atomic mass, for the atomic number, I'm sorry. So he developed the term atomic number. It's kind of the number of the atom in the series, and it was kind of important thing for the periodic table and for the understanding the periodicity of elements, because as I said before, it was first depending on the atomic mass, not on the atomic number. So when it started with the atomic number, it made everything clear and very understandable. So now we are done with the most of the part of exploring the nucleus and the structure of the atom. Still, there are some details about the electron and the way the electrons rotate around the nucleus, and this is what we're gonna discuss in the next video, inshallah. So I'll see you then. Goodbye.